Hi, this is Mr. Anderson. Today I'm going to talk about the properties of matter. What is matter? Matter is anything that has mass and takes up space. But in this podcast, we're going to talk about large-scale measurements of matter. So how large could we get? Large enough. If we talk about this is actually, if we were to look up in the constellation Pegasus, we'd find this. This is a binary system where we have this star, which in relation to our sun is much bigger. It's called IK Pegasi b. And then we have this tiny little thing, which is a white dwarf. What is a white dwarf? It's essentially a star that's lost enough of its mass or lost enough of its energy to kind of go dark. The cool thing about white dwarfs, they've always fascinated me, is they have a huge amount of density. In other words, if we were to look at this one white dwarf right here, it has about 1 × 10⁶ grams per cubic centimeter for density. What does that mean? 1 cubic centimeter of this would have the mass of 1,000 kilograms. So a tiny little bit like that would weigh 1,000 kilograms. So that's pretty amazing. Eventually this will go red giant. This stuff will go into here and could explode as a supernova. But I'm getting ahead of myself. So first of all, let's talk about what density is. Density is essentially mass per unit area. And so I like this because it's a quick way to remember density. I've got mdv here on the bottom. And so let's say we had a cube of water that looked like this, and that cube of water was 1 centimeter by a centimeter by a centimeter. So it's 1 cubic centimeter. The mass of that would be, we'll say 1.00 grams. The volume would be 1.00 centimeters cubed. And so it would have a density of, well, let me stop for a second because you can use this pyramid. And so what you do is you simply put your finger in the start of the one that you want to find. And so in this case, if I cross out density, this tells me that the density is simply the mass divided by the volume. And so if I take the mass, which is 1, divided by the volume, which is 1, it's going to give me a density of 1. So let me scratch that. Get significant digits right. 1.00 grams per cubic centimeter. Okay, so another thing you could do is, let's say I'm given the density, but I want to find the mass. That mass is simply going to be the density times the volume. Or scratch that. If we want to find the volume, I cover that up, and that's going to be mass divided by the density. So that's pretty cool. What do we know about water? Water is something that's really weird. And so if I were to have that same cube of water and put it in an ice cube tray, it would actually increase the volume. So the volume would be greater than 1. And that's because ice actually has a density of 0.92 grams per cubic centimeter. That's why ice floats, but we'll talk more about why it actually does that later. So now we're presented with the idea of Archimedes. Archimedes had this dilemma. The king told him that he wanted him to figure out if the crown that he'd asked a craftsman to make was actually made of gold, or if the person had actually slipped in some silver to save himself some money. And so the story goes that Archimedes thought about this for a long period of time, and then eventually he's taking a bath, and he realizes the right answer and how to solve it, and he jumps out of the bath and runs through the streets saying, "Eureka!" In other words, I've discovered it. And so what did he discover? It's a pretty cool idea. He discovered Archimedes' principle. And so Archimedes' principle goes like this. What he discovered, or his idea, is that he could have a balance where on one side of that balance he puts the crown. So let's put the crown like this. And then on the other side of the balance he puts a weight of the correct amount of gold. And then he just kind of balances this whole thing in water. And so what he could look at is the buoyant force. In other words, in a perfect world, the buoyant force of the gold and the buoyant force of the crown will be the same. But if it's somehow unequal, then he knows that the guy is trying to cheat the king. Okay, so what is buoyancy? Buoyancy simply is a way to think about it. It's a fluid that you're immersing something in, saying, I don't want this, and trying to throw it out. And so example, this right here, this oil tanker is made of steel, and steel's going to sink. We know that. And so how is this oil tanker able to float? Well, that oil tanker is displacing water. And by displacing the water is exerting a force on that. We call the buoyant force up. And so this does a little bit better job than that. When you put an object in water, there's a force of gravity pushing it down, but there's also a buoyant force equal to the weight of the fluid you displace. And so by making the volume bigger, in other words, decreasing the density, we can make something float that normally wouldn't. So that's buoyancy. Buoyancy in gases works a little bit differently. Buoyancy of gases is a direct relationship. And now we have one of our first laws that you should remember, and this is Charles' law. Charles' law says this, that as you increase the temperature, there's going to be a direct relationship with the volume. And so if we look at this apparatus over here, if I were to somehow crank up the temperature in here, that's going to make the molecules move around more quickly, and that's going to increase the volume. And so example of this is my friend Scott Taylor. He's got a balloon in town. And as he heats up this balloon, he increases the volume of it, which decreases the density, and that makes it float. If he wants to come down when he's done with the balloon trip, all he does is quit firing that propane tank into it, and that's going to decrease the volume and thereby decrease the density, and so it's going to sink. So Charles' law, there's a direct relationship between volume and temperature. Next thing I should explain is what's called pressure. Pressure, think about it like this. Inside an object, pressure is the force of all those molecules pushing out on it. And so the SI unit for that, in other words, in science we measure that in something called a Pascal, which is named after this guy, Blaise Pascal. What is it? It is the force of 1 Newton. And a Newton, the way I always like to remember a Newton is like the weight of 1 apple. The weight of 1 apple on 1 meter cubed. And so a Newton is not very big. So normally we measure, instead of pascals, we measure in kilopascals, which is going to be 1,000 pascals. And so the best barometer, the most simple barometer, all you do is in a tank, you put some mercury, and that mercury goes up a tube like this. And so as the, let me change color for just a second, as the air pressure pushes down on it, it pushes that mercury up in the tube, and so it's a way to measure air pressure. And air pressure is incredibly intense. We don't normally notice it, and that's because we just are surrounded by it. But imagine if we go deep down into the ocean, that pressure is big enough that it can actually crush us. So that's pressure. But it finally brings us to what's called Boyle's law. And Boyle's law says this. If we've got pressure and volume, we'll say right here, and we increase the volume, so we're going to increase the volume of that object, what happens to the pressure? The pressure is actually going to decrease. Or a better way to think of it, if we have all of this gas that's got a really big volume, but we were to somehow squeeze it into this little aerosol canister, which has a smaller volume, then it's going to have a way greater pressure. And so it's going to exert that pressure out. So Boyle's law looks like this. In other words, as we increase the volume, we're going to decrease the pressure. Likewise, if we have a given amount and we decrease the volume, then we're going to increase that pressure. And so these are simple ones that you can actually solve some quick equations if you know Boyle's law. The 1 and the 2 represent the pressure and the volume initially, and then after something happens. Okay. Last thing I want to talk about is called viscosity. Viscosity is resistance to flow. And so resistance to flow in a material. In other words, something that has a really high viscosity would be silly putty. Something that has a really low viscosity is going to be water. In other words, it easily pours. Something that has a viscosity somewhere in the middle is going to be honey. I love this picture right here. What they've done is they've actually taken some silly putty, and if you put that silly putty on a table with a small hole in it, it'll eventually, since it has really high viscosity, will flow through here, and so you get kind of this drooping thing coming through it. One interesting thing I learned when I was growing up is that windows, the glass that we used to put in windows, the glass is actually a liquid. It's a really high viscosity liquid. And so if you go to old windows in old houses, you'll find that they're actually thicker at the bottom, and that's because the glass is actually slowly oozing down to the bottom. And so those are some of the properties of matter. Big things we talked about, again, is Archimedes' principle and buoyancy, but also Charles' law and Boyle's law. And so hopefully that's helpful.